Greetings, geometry students. Today we're going to continue on with our new exploration of vocabulary inside of circles by looking at another type of angle that may appear, and they are called inscribed angles in circles. Please copy down your title as well as your objective. And our objective for the day is to learn the relationships between an inscribed angle and its circle. Anytime you need more time, press pause and then hit play when you're ready to move on. Okay, so let's take a look at inscribed angles. Now here's your definition. An inscribed angle is an angle in a circle that has its vertex on the circumference of the circle and its endpoints on the circle as well. Now I'll give you a diagram to accompany this definition. A typical inscribed angle might look like this guy. As you can see, the difference between an inscribed angle today and a central angle from before is, of course, a central angle had its vertex positioned on the center point of the circle. It would have been on point D. However, an inscribed angle does not want its vertex on the center. Inscribed angle wants its vertex on the circumference of the circle. Okay, so in this particular case, we would be able to identify that angle ABC is an inscribed angle of circle D. Now, this is a little repetitive from the other day because the same conditions do apply. Just like with central angles, an inscribed angle intersects a circle at two places. We talked about arcs last time. Those two endpoints of angle ABC up there intercept an arc on the circle. And of course, we talked about arcs, that arcs can be minor arcs if they are less than half the circle, or major arcs if they are more than half the circle. So review that information if you have forgotten it. Now, just like before, there is a relationship between the angle measurement of an inscribed angle and its intercepted arc. And the relationship between those two, it's not that they are equal like the central angles were. Okay. This time the relationship is that the measure of the angle is going to be exactly half of the measure of the arc. Or if you want to reverse that thinking, you can think of it as the measure of the arc is always going to be twice as big as the measure of the angle. Okay, so using the same diagram that you copied a moment ago, you do not have to copy it again. You may state that the measure of angle ABC is going to equal half of the measure of arc AC. Or as we said, you could also state that the measure of arc AC would equal twice the measure of angle ABC. So two different ways of thinking of the same thing. It's just an issue of whether you want the 1/2 over on the right, or if you want to multiply both sides by 2 and have the constant over on the left side. Either way would get the same thing. And of course, keep in mind that our angle measurements and our arc measurements are still both going to be measured in degrees. Now, there are some special situations that go along with inscribed angles, and that's why we held off on them. Central angles are a little bit more straightforward. Inscribed angles have a couple of little catches to them. Okay. One of these, and these are both theorems. Okay, and remember, a theorem means it is not necessarily common sense. It is something that somebody has taken great pains and labors to actually prove. But I think you'll see that these are very much common sense type statements. Anyway, the first theorem, if two inscribed angles were to have endpoints intercepting the same arc, then those angles would be congruent. Now, if you think about this, this makes perfect sense. Two inscribed angles ending at the same endpoints on a circle, then the angles would be congruent. Well, that actually does make perfect sense. Here are two inscribed angles, and as you can see in the diagram, they terminate at exactly the same endpoints on the circle. that means that the arc measurement in between those endpoints is the same for both angles. Well, if the arc measurement is the same for both angles, and there's a relationship between the angle measurement and the arc measurement, then it's going to force the two angles to be congruent. Okay, so that's really not all that groundbreaking math as far as a statement is concerned, but it is one of the theorems we're expected to discuss, so there it is. Okay. Another one that is kind of common sense, if you think about it for a moment, is this other theorem, or the second theorem that we're going to look at. There are three. Okay. And this one says an inscribed angle will be a right angle if its endpoints are on a diameter. Now, we haven't spent a lot of time talking about a diameter this year. We'll get to that vocabulary here before long, but that's one that you're familiar with from back in elementary and junior high. Okay, and this one is common sense as well. We're basically saying if an inscribed angle measures exactly 90 degrees, then that means its endpoints are on a diameter. Well, a diameter cuts a circle exactly in half. That means that the circle is a semicircle, half of a circle. How big is half of a circle? Well, an entire circle measures 360 degrees. Half of that would be 180. So if the inscribed angle has an arc that measures exactly 180, and the inscribed angle has to be half that big, then obviously the inscribed angle would have to be 90 degrees. So thank you very much for the theorem, but this is really something that we could have figured out on our own. Okay, the third and final theorem that we're looking at today is this one. This one's a little less obvious, but still could be figured out without the statement. A quadrilateral can be inscribed, and the word inscribed may be one that you're not familiar with. Inscribed means a shape that fits perfectly inside of another one. If a shape fits perfectly inside of another one, we say that that shape is inscribed inside of another shape. So a quadrilateral can be inscribed in a circle if its opposite angles are supplementary. This one's less obvious. I'll explain it to you in class so you can get a good idea. Okay, but here is an example of a quadrilateral that is inscribed inside of a circle. Now you just have to trust me for the time being that this theorem says, okay, angles 1 and 3, which are opposite of each other, says they must be supplementary. So angle 1 plus angle 3 adds together to equal 180 degrees. And same thing for angle 2 and angle 4, that they must add together to be 180 degrees. Okay, so it's saying that when a quadrilateral fits perfectly inside a circle, all of its angles are inscribed angles inside of the circle, then a condition that's going to apply is that the opposite sets of angles will be supplementary, as is stated on the sheet or the screen in front of you. Again, that one's not so much common sense, but when we come to class, I'll show you how this one works. Okay. Now, just like yesterday or last time, we are looking at an example. I want you to copy down the circle A that is shown here, including all of the line segments bouncing around inside of this circle, all of the angle measurements that are provided, and then I have 4 questions that I would like you to think about and respond to before coming to class on the day that the notes are due. Okay, so copy down circle A, and I have 4 questions for you to consider. Okay, I'm going to leave the video running for a few seconds so that you will have time to copy down the diagram. However, the audio ends now. I appreciate you finding time to get your notes done, and I will see you in class. tastes like hell.